let's discuss one of those two fundamental challenges, namely handling collisions. So we have the issue that multiple objects might end up with the same numerical representation. For example, we had gross pi and boss pi. So you might just think, well, couldn't I just write a really clever function that will ensure that everything has a unique number? But it turns out that's an impossible goal. So let's discuss that first. So I'll make a note that the biggest array in Java is 2 billion entries. No matter what, you can never, ever have an array bigger than that. Therefore, having a hash code that is, you only have 2 billion different hash codes. And so this is a handy idea known as the Pigeonhole Principle, where it says if there's more, you can think about it this way, if there's more than 2 billion possible items, then it's just natural that there has to be at least 2 things that have the same hash code. So it's drawing from here. If I have 9 different possible boxes that a pigeon can go to, and each of these pigeons has in its brain, like, I would love box 0 or 1 or 2. If I have more than 9 pigeons, it is necessary that one of the boxes is going to have more than one pigeon, right? You can just see it. There's no way I can rearrange these pigeons so they all have their own home. It is sad. Sorry, birds. So likewise, in Java, well, let's take planets, for example. There's more than 2 billion possible planet objects. Each has a mass, an x position, a y position, a x velocity, a y velocity, an image name, possibly more stuff depending on your definition of planet. There's more than 2 billion possible planets, so it is natural that at least 2 planets will map to the same hash code. It doesn't matter how clever you attempt to be, there are 2 planets. They're going to have the same hash code. Okay? So basically, I just want to let you know that we can't avoid collisions just by having a clever hash code. It's just not going to happen. Okay? So what we could do instead is look at nature for inspiration. And we say, what do these pigeons do? Okay, well, we just put 2 pigeons in one box. Okay? Well, we're going to do the same thing. Instead of storing true-false values in a particular bucket, then we're going to store a list of the items that are in that bucket at that position instead. Okay, and we'll see an example in a moment. But basically, instead of true-false, we'll have a list of things. How do we implement that list? Well, the easiest way is just a linked list. But you could also do, say, an array list. Or if you wanted, you could use something that's not even a list and like a set. But we're going to focus on the linked list because it is the simplest thing conceptually. Okay. And so the approach, this idea of taking each bucket and instead of storing true-false, storing a list of all of the items, that is known as external chaining. Okay, and that basically says that, so let's take, for example, we've put cat, dog, snack, potato, rotato, and totato into some kind of hash table. Well, in this case, potato, rotato, and totato, if we use that same calculation we did before where you use the bottom 5 bits for the O, the next 5 bits for the T, and so forth, potato, rotato, and totato will all end up in the same bucket. But rather than saying true or false, we're actually going to make a list of those items. Okay? So if I want to know, is rotato in this list? Well, then I would compute this number, and then I would check each of the items, and I would say rotato is here. So let's think about the performance of this scheme. These are all of the numbers from earlier in lecture, and this is this new scheme, this external chaining hash table. Now we'll notice that unlike the data indexed array we had earlier for integers, now instead of having true-false, we can have a list, and so the runtime, instead of being constant, will be big theta q, which is the length of the longest list. That's the worst case. Okay? So in this data structure, the worst case would be 3 in a way, right? We would say, in the worst case, we have to look up totato. Okay? So that's external chain. So this approach has the advantage that it handles collisions, but we'll also see that it's going to help us a lot with our memory usage. Okay? So let's see why that is. Here's a little puzzle for you to ponder that I won't talk about during the video. So I'm going to make a note that we don't really need 4 billion buckets for all this stuff, right? We don't, look at all these buckets we're not using. We're not using this bucket, bucket number 553 million, right? We're not using that bucket at all. In fact, we're only using a very limited number of buckets. And so an open-ended question for you might consider is, let's suppose we just say we only want 10 buckets. And think about how we might place each of these items. Okay, so just use your intuition. Okay, so I'm going to make a note that really, we could just use, for example, there's many possibilities, we could just use the bottom digit of that number we calculate. So we could just say, okay, you know what? We're going to mod our hash code by 10. We're going to say potato, rotato, and totato. Those all ended in 1, so we'll put them in bucket 1. Dog, that goes in bucket 3. Cat, that goes in bucket 4, snack that goes in bucket 7. Okay, and so we could compute, after the hash code, we could do a second pass where we take the number and we throw away some information. Now you might say to yourself, but Josh, doesn't that mean we're not really using this upper data here, like potato, like this is basically getting thrown away? You're right. We'll talk a little bit more about that in the next segment of this lecture. But you can see here that we can take the hash code and put things in buckets, like so. Okay. So this right here, we are saving. We're going from an array of size 2 billion to an array of size 10. And at least for this data set shown, we incurred no hit in performance. Okay, so that's pretty good. However, if you start inserting more items, eventually you're going to start getting buckets with more and more stuff. Okay? So I'm going to introduce a term known as the load factor. So if we have n items, in this case n is 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We've inserted 11 items into our data structure. And we have m buckets, in this case 6. We'll say that ratio, n divided by m, 11 divided by 6, 1.83, is the load factor. So on average, the average list in this data structure is length 1.83. And so if we're concerned, we start thinking about not the worst case runtime, but the average runtime, we can say, okay, well, the runtime of accessing something in this data structure should be big theta L. Okay? And so I'll make the obvious observation that as long as L is small, then our data structure should be really fast. Assuming we have things nicely spread out and that L is small, like this, then our data structure will be quick. Yes, technically, the runtime is going to be related to the length of the list, but if our lists are all short, that's fine. So here's a question. As n grows, what can we do to ensure that L stays small? So imagine I keep adding more stuff. It's like, this thing's getting, there's like 100 items in each list, 1,000, and so forth. What can we do to ensure that L stays small? So think about that for a moment. Okay. So I say that we can take a cue from our array deck, so we can actually resize. When our load factor becomes too big, we can say there's too much stuff here, so we'll make a bigger set of buckets. We'll maybe double the number of buckets, say. Okay. So here's a question to ponder, and if you're watching the video, you obviously can't submit to pull everywhere, but I do want you to think about this question. Okay. So let's suppose we have these pictures, right? So pictures, just like strings, can be turned into numbers. And let's say the hash code of this axe is 0, the hash code of this bow is 0, this helmet is 1, and this apple is 3. And then again. The axe's hash code is 16, the bow is 20, the helmet is 13, and the apple is 7. But if you modulo each of these numbers by 4, you end up with the appropriate bucket shown, right? So 7 mod 4 is 3. So the load factor of this table right here is 1. But let's say I resize this, this data structure to size 6. Where will the apple appear? Okay? And the difference is what you're modding by. So ponder that for a second. I'll wait for you. Okay, so after resizing, after I make more of these buckets, in the new universe, apple, well, 7 mod 6 is 1. 13 mod 6, also 1. 20 mod 6, 2. And 16 mod 6 is 4. So in this case, apple, axe, and bow used to be buddies, but now apple and helmet are buddies, and axe and bow are separate. Okay? So when you resize, you're basically going to build an entirely new data structure, copy everything over, but the result after you're done, you do one costly resize, but once you've done that, then we have a data structure which should be hopefully fast. Let's consider one last little tricky situation, which is what happens whenever we have a hash code which is negative. So in Java, hash codes are allowed to be any integer, which includes negative numbers. And so a question for you is, which bucket do you think is most natural for this apple to live in? Okay, it's a philosophical question. Okay, so I say 3, and my argument is as follows. Just as if something has hash code 0, it should obviously go in bucket 0. If it has hash code 1, it should go in bucket 1. If hash code 2 goes into 2, hash code 3 goes into 3. And if it's hash code 4, well, we loop back around and come up to 0. Now if we go in reverse, well, 2 goes into 2, 1 goes into 1, 0 goes into 0, and I say minus 1 ought to go in 3. That's just my philosophical decision. That's not the way you have to do it, but that's the way I want to do it. Well, what that means, though, that we want to consider is, well, we said using the modulus operation might be a good idea. And so the question is, what happens if you try to take this apple, take its hash code -1, mod it by 4, and try and put it in this array. What do you think will happen? Okay. Well, it turns out that -1 mod 4 is -1, so it'll try to put it in bucket -1, which will be an array index out of bounds exception. And so that's one of the challenges you're going to have in Lab 9. Okay, just throwing that out there. So let's summarize the key details of this so-called hash table. Okay? So this data structure we've designed so far is called a hash table. What are its features? Well, every item you might try and put into a hash table is mapped to a bucket number using a hash function. What's the hash function? Well, it's a two-step process. Okay? What it does is it takes an object, like a phone or whatever, or a pen, or me, and it comes up with a number that represents me. In a two-step process, first we compute a hash code, which every Java object has to be able to do, which is some integer. And then we take that hash code and we turn it into a bucket number by computing the hash code modulo m, taking into account that funny issue we just had with -1. So negative numbers, you have to do something a little different. Okay? We also have this important point, which is that if L, which is the load factor, which is defined as n divided by m, where n is the number of items and m is the number of buckets. If that becomes too large, then increase m, which will obviously reduce the load factor. Okay. And so if multiple items happen to map to the same bucket, which can certainly happen. Another important point is we have to resolve the ambiguity somehow. And so there's two common ways. One is the one we just discussed, where we create a list for each bucket. And there's another in the extra slides called open addressing. It's not necessarily better, it's in the extra slides, but I have mentioned it and made a slide because it could come up at a job interview, but we're not really going to talk about it at 61B. So, you should be asking yourself, what good are hash tables? So it's been in a lecture so far, but maybe let's draw that out and make sure it's very clear exactly what we've gotten out of this. Okay? So let's consider the performance of a hash table. So what we built is a data structure where whenever we insert an object, we figure out what number bucket it belongs in, and then we throw it into the list corresponding to that bucket number. And so if we look at the average case time, the time it takes to actually insert or check if something's in this list, well, if we have a fixed size list, or if we have a resizing list, it is certainly the case that the time it takes to actually get something back out of this table or to insert something into it should be proportional to L, the length of the average list. That's what the load factor is. Okay, so in the average case, it takes L time to get something. How does that compare to our binary search tree, a balanced binary search tree? Well, in that case, the average case, and in fact also the worst case, was log n. But here, in the hash table case, it's L. But what's L? How's L in terms of n? And well, it depends. It depends on whether or not we have a fixed size for resizing. So in a fixed size table, we basically have 5 linked lists here in this case, if m is permanently 5. So if we have 1 million items, well, we have one list that's roughly 200 million long. Wait, let's see. If we have 1 billion items, and we have one list that's 200 million items, another that's 200 million, another that's 200 million, another that's 200 million, another that's 200 million. And so the runtime for those is going to be really slow because we're going to be going through a big long list. If we're doing resizing by contrast, if we make sure that the length of each list is a constant, that is, that the load factor is never above, say, 5, so that if I have 1 billion items, I now have 200 million buckets. In that case, my load factor is still actually my load factor is going to be a constant, right? So if structurally I decide to always have enough buckets so that the average list is constant size, then the average list is going to be a constant size. And so what that means is that external chaining with resizing, its overall contains and insert runtimes will be big theta 1, okay? Amortized, because I have to take into account all of that resizing that goes on. What's more is these items don't even need to be comparable. I don't have to say that one's less than or greater than the other, and so I get some advantages. Now what's ultimately going to be faster? It's going to depend on your application. You'd have to do some kind of profiling to say that my hash table is definitely going to be faster because there's a bunch of things going on. I have to compute hash codes, there's the resizing, and so forth. Though, basically what will happen is that both a tree-based and a hash table-based implementation will both be really fast, with probably a slight edge going to the hash table. But kind of depends on your application and how you're computing hash codes and so forth. Okay, so it's just an alternate way that we can build a table, but not strictly better or strictly worse. Now, one last little detail about this performance. I've been talking about average case, but the performance is going to depend on the number of items in each bucket. There's a big difference between these two pictures here. They both have the same load factor, right? The load factor is 1. There's 1 item per bucket. But here I have a long list, and here I have a bunch of stubby lists. And so while the average runtime, you might say, of each of these things is L, average isn't, of course, the whole story. We want some kind of balanced buckets. And so this process is analogous to maintaining bushiness in a BST, but conceptually it's a lot easier to solve than the mess with tree rotations and the isometry between red-black trees and 2-3 trees. So in this case, it's going to be an easier problem to solve. But that's what we're going to get into now, is talk about this issue of how we can maintain a balanced list, meaning pick good hash codes.